Question 3, F324 June 2012. This question then about fats and oils, and it says that some fats contain glyceroids and steroids. As usual, this is a little introduction to what question 3 is going to be all about. First of all, we're going to look a little bit at triglycerides, and then we're going to move to look at cholesterol, which is a steroid. So in part A, you've got trans oils, which have health risks. We normally call them trans fats. The only difference here being that these must have shorter chains, so a lower boiling point, so they're liquid at room temperature. You've got the structure shown of octa, deca, 12NO8, which is a trans oil. Bullet points want you to add the double bond to the structure and state how the trans isomer is different from the cis isomer. So here what I've done is I've numbered up my carbons from my carbon here with the C double bond O. That's where your fatty acid, if you like, starts, because here you have what used to be the carboxylic acid. It's now been made an ester link to make a glyceride. Now that's where your fatty acid would start. So 12NO8, you've got 1 starting 2, 3, 4, 5, 6, all the way to 12. So you place your double bond there between, or from 12 to 13. Now, second bullet point asks, how does the trans differ from the cis? So which version have we got here, cis or trans? We have the trans version, don't we, because you've got the two different branches on opposite sides. So if you were going to have a cis version, you'd simply have a situation where both of the branches, or both of the hydrogens, which you'd have us show in structural formula, are on the same side. So to answer that second part of the question, to pick up the mark, it would be sufficient to draw that diagram, but I think it's worth also adding some words to it. And so we've got something like in the cis isomer, both branches are on the same side. So you've got written in words now what you've shown in the diagram. The cis isomer, in the cis isomer, both branches are on the same side. In the final part of this section, it states 1, the health risk of a diet which that is high in trans oils or trans fats. The answer here could just simply be heart disease, but from what we've seen in the mark scheme for more recent June 13, it's also important to mention that trans oils can cause an increase in bad cholesterol. That's LDL, low density lipoproteins. So it's that they were looking in June 13 for that keyword cholesterol. So what's the problem with trans fats or trans oils? They cause heart disease. Trans oils can cause an increase in bad cholesterol. Now in part B, where we start looking at steroids, if I told you that this was a real question, you'd probably think it was a joke in class. Here's the structure of cholesterol. How many carbon atoms are there in a molecule of cholesterol? This is one of those one markers that it's pretty difficult to pick up, really. So let's just have a look. I'm just going to count around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. the point where I'm thinking, am I going to get the right number? 11, I'll do 12 there, 13, 14, yeah, I've lost my cursor now, oh no, here we go, 15, 16, 17, 18, let's go back here, 19, 20, 21, 22, 23, 24, 25, 26, 27. Fantastic. My answer then is 27, and I would, if you got another one of these questions, recommend counting round like that. It just saves missing one out. Now, having said that that question was a bit of a joke, you've now got to look for the chiral centres in a molecule of cholesterol, and this again is not going to be easy because there's a lot, and I'm actually going to clear this page off so that we can. Oh, have I deleted the whole page? Maybe I have. Oh, that was maybe a bit stupid. Okay, so now I've got my page back and it's cleared. I'm looking for chiral centres. So chiral centres, remember, you need how many different groups attached? Yeah, you've got 4 groups attached. Remember, skeletal forming, you can never see the hydrogen. So here I've got this carbon, I've got an OH, and I've got a group going around here which comes to a sort of methyl there, and a group coming around here which goes to a double bond. So those two are definitely different, and I've got an H there as well. So I'm going to put a little asterisk there to show that that is a definite chiral carbon. Then coming around, this one's got 2 hydrogens, so no. This one's connected to a double bond, so no. This one also connected to a double bond, so no. This one, 2 hydrogens, so no. This one, potentially, it's got 1 hydrogen there. This is coming around to a double bond. This is coming around to a different section of the molecule. This also is coming around to a completely different section of the molecule. So I'm going to place an asterisk there. Going on, let's have a look. This one, again, it's got 1 hydrogen. This is going off to one part of the molecule. This is going off to another different part of the molecule. This again is going off to a different part of the molecule. So another asterisk there. Notice that none of these are going to exactly the same thing. They're all obviously all part of the molecule. If I start here, I get to a different place. And if I start here and go to there, I get to a different place on the molecule. Going round then, 2 hydrogens, 2 hydrogens on there, 2 hydrogens on there. This one looking like a potential. You've got off to that long branch there. You've got around that side, which is different from around this side. So that I'm putting as chiral. Coming up onto here, a methyl, a long chain, and a great big set of. So that also chiral. Around there, all 2 hydrogens on those. Those 2 groups are the same, so nothing else on that branch. Let's go around here. We've definitely got 4 different things here. A methyl group off to the rest of that molecule, off to the rest of that molecule in a different way. So that double bond which changes things. And again off to the molecule here with the branch, so I'm going to put that one as being chiral too. Then round 2 hydrogens, so no. Another potential here, because it's going off in all different directions. So one there. I love it when I lose my cursor like that. Hopefully it won't crash before I finish this question. And we've got one last one which I can't actually put my cursor on now. Let's see if it'll come back. There we go. This final one here, isn't it? It's going to be a chiral centre as well. So I've marked those 2 together. Look at that. That's beautiful, isn't it? So counting those up, 1. I'm afraid I've not got my cursor to point, but you can do the counting for me. 1, 2, 3, 4, 5, 6, 7, 8. And I make it. So let's just put that answer in. I have, oh, isn't that interesting now? That's moving off there. I probably won't be able to write this answer in. Go on, let me do it. 8. Look at that. In the final part of this question then, part C, we've got a molecule which is crossed between an ox and a rolo, oxandrolone, and we've got to first of all see what functional groups are in it. So we're looking over here, we've got lots of rings which make up our steroid, but then we've got this OH here from alcohol, and here be careful, you've got a C double bond O, and you've got an O, so this is an ester link. Don't be fooled by the fact that it's a cyclic. You can have cyclic esters too. If you've got a C double bond O and an O next to it, then that's your ester functional group. So you've got here 2 marks. I'm going to put it in text because I don't trust my pen. We've got an ester and alcohol. 2 marks there. Oxandrolone is synthesized from naturally occurring steroids, suggests an advantage of developing a synthetic route to produce it. Well, if you've got naturally occurring steroids, they naturally occurring molecules always have the same chirality. So if you're producing something from a particular chiral arrangement, the resulting molecule will be in the same chiral arrangement. So you ensure correct chirality, and also obviously if you're using a particular chiral molecule to synthesize, then you're going to only correct chirality also implies that you're going to have a single optical isomer, or the other way of optical isomer, enantiomer produced. So you ensure correct chirality, a single optical isomer is produced. Obviously that optical isomer is the one with the correct chirality, the right arrangement of atoms. So then compound C below is an intermediate formed during the synthesis of oxandrolone. Remember that we've said from the previous question that oxandrolone had that cyclic ester. So we had a O with a double bond connected to an O in the loop. I'm just trying to think how how it looks. And I lost my cursor too. So there you had what used to be, or is going to be made into that cyclic ester. You've got here the intermediate compound C, which has these 2 functional groups here, a carboxylic acid, here an aldehyde. So in the part of the question then you're asked, suggest a 2-step synthesis of oxandrolone from compound C. So you've got to make the ester from the 2 functional groups you've got here. So from there, this part of the molecule has to become your ester. For each step of the synthesis, state the reagents and conditions. So important here, you've got stating the reagents and conditions. But notice what it's not saying. And also state the functional groups. It's important to state the functional groups that would react and those that would form. So what it's not asking you to do is write an equation. At no point here do we need to write an equation. We need to state functional groups, which means we need to name them. And it's so important this masking, they wanted to see the names of the functional groups and those that would form, and it just wants reagents and conditions. So looking at these functional groups, we've got a carboxylic acid here how do I form an ester? For an ester, I need to have carboxylic acid. I also need to have alcohol. And I can just do my esterification. Conditions for esterification I need. But I've not got an alcohol here, I've got an aldehyde. So I've got to get my aldehyde to become an alcohol. Which reaction can I use to do that? And I need those conditions. So coming to answer the question, we've got then textbooks. Yeah. We've got then, first of all, I'm going to need to turn aldehyde into an alcohol. So to do that, my conditions, I will need my sodium borohydride, and that's all I need condition wise. In that reaction, which is a reduction reaction, I will use water as a solvent and I will warm it, but generally the mark scheme ignores those two facts and just wants you to have the sodium borohydride. But it must be useful to have in the back of your mind water as a solvent, so you could put aqueous and it would be warmed. But we've got enough here. That's the condition. I've said already what I need to put in. I've got aldehyde, produces alcohol. That's my first reaction. I now have an alcohol, so I'm going to be doing an esterification. Our condition for esterification is conc H2SO4 and reflux. Then to finish off, I just need to state again the functional groups. So I've got a carboxylic acid and alcohol produce ester. So that question, I would have thought in this exam, many people lost marks because they did not say simply, well, they probably stated reagents and conditions, but this second bullet point is, you have to read so carefully because most people have written equations here. State the functional groups. Don't be lazy, write them out, and if you like, give them an actual formula, displayed formula, but make sure if it's saying state functional groups that you're doing some writing. So I think many people lost marks from being lazy there or not reading the question.